Okay. Hello everyone, thank you for coming to watch all of our presentations. My name is Hale, and here is my son Capstone. So a little bit about me. I'm a senior at Grandview High School. In terms of workload, by the time I graduate, I'll have done 10 APs and differential equations / calculus 3. Some of the APs include Physics C and Physics 1. I do a lot of theater. I counted, out of the 12 main stage productions I could have done across 4 years, I've been in 10 of them. Here's a picture of me in sophomore year. In fact, I just finished this year's play, Holes, where I played the main character, Stanley. This year, I counted, I've spent over 300 hours after school doing theater just this year. So, it's a lot. In next year, I plan to go to Colorado School of Mines to study nuclear engineering. So, nuclear engineering, what an interesting topic. There's been some new things about nuclear engineering recently. There is new developments in fusion technology, which would be really cool, which brings me to my project. I wanted to make a robot that folds origami. Nothing to do with nuclear engineering at all. Which brings me to the question, why origami? Well, one of my biggest inspirations for engineering is the YouTuber Mark Rober. He used to be a NASA engineer, but now he makes silly engineering videos on YouTube. As you can see, this is one of his robots. It's a robot that can put together a puzzle, but as you can see, it has little googly eyes, so it's fun. These are from Mark Rober. They're called Hack Packs. It's a kit that's sent to your house that you can put together in code, and I've been putting some of them together just in my spare time. But why origami specifically? I went to Liberty Middle School here, and in 7th grade engineering class, I would get all the work done pretty fast, and then me and my friends would be bored with nothing to do in class. So, we decided to fold origami, and we learned a bunch of origami stuff. I've forgotten all of them except paper cranes and a cootie catcher. So, I thought it'd be a good idea to, since I started engineering with origami, I thought it would be a cool STEM capstone to do a engineering origami-based project. Project objectives. Number 1, I wanted to round out my engineering. I have taken Engineering Tech 1 and Computer Aided Design. I have my CSWA, but that's really all. So I can create, I know how to use SolidWorks and I can create digital parts, but I didn't really know how to code or the electrical engineering part of it. 2, I wanted to re-foster some creativity. I express creativity in theater, obviously, but in other classes, I find them lacking in creativity. So I wanted to harness that creativity to make this project. 3, professionalism. That's cool. I didn't check my email, at all. I think I have 100 notifications on Toluchi that I just haven't looked at. So I wanted to work on my professionalism. 4, time management. With all the theater and all the class load, it's a lot of work, so I wanted to work on my time management, and with that, stress management as well. So for my advisors, my expert advisor is not here today. He is currently teaching at CU Boulder, but his name is Leopold Buchan. He is, as I said, he's a professor at CU Boulder. He specializes in robotics and mechanical engineering. My support advisors, my 2 parents, they give me money and food, I guess. And then my last support advisor is Riona. She helped me with editing and spelling and sending emails, because I would draft up an email and be like, oh, I hate this email, it's stupid, I'm just going to delete it, restart it. And before I could delete the email, she would send it for me. So, this was my initial plan. And I did not use this at all, but I wanted to show it for 2 reasons. 1, humble beginnings. I wanted to show the contrast between my initial plan and my final plan. So what this was is I wanted to use magnetic paper, electromagnets, and a foldable bed in a robot arm. I don't know why. I don't know why I went this direction, but that was my initial plan. I think this is funny because my solution for folding a piece of paper was to fold a different surface. We're not getting any closer. The other reason I want to include this is because I actually had a second expert advisor, but after he saw this design, he stopped answering my emails. So I just wanted to include it to show the full story. My initial project timeline, in October I wanted to learn Python as well as in November, then research the electrical components I need to use, brainstorm the design, build it in CAD, implement the code, and then testing and improving and making the presentation. Like many other projects in this class, our initial timeline, very optimistic, very hopeful, but not very accurate at all. And we'll get to that. So research. The first research I did was coding. Originally, I was going to code in Python, but after meeting with my advisor, he said that I didn't need the computing power of a Raspberry Pi. Instead, a Arduino would be much better suited for this project. And if I wanted to use an Arduino, instead of learning Python, I would want to learn C++. So that's what I did. To do this, I went to Tinkercad. Tinkercad I could multitask because they have electrical components. This is a digital workspace where you can drag in electrical components like wires and an Arduino and put them together to learn the electrical engineering components. And I also had code. So, and not only did it have code, it had code in little blocks, like Scratch, if you did that in elementary school. So let's break down the pros and cons. The pros, I can code and do electrical engineering at the same time. That's great. I can do it virtually. I don't have to wait to buy it and come in and then realize, oh no, I don't have a right resistor to learn the next concept. And I can code through blocks, because coming into this, I have no coding experience, so doing it through blocks was great. Cons, wasn't very relevant. Some of the tutorials was like how to code a light sensor, or a temperature sensor, or a motion sensor. And while they were interesting and helped me develop the electrical components, it wasn't very relevant from a coding standpoint. And so I'd have to come back to the coding standpoint. Going forward, I was falling behind in my timeline, and so I thought, hey, let me make all the parts, and then I can come back and learn how to code a motor. So research. Here are some examples. The first one is from Namiki Laboratory from Chiba University. It has like grippy little fingers, which I don't know if it's just me, makes me kind of uncomfortable, and I'm not sure why. It's very complex and kind of inaccurate. After they make this fold, they show it off, and it's just slightly askew. It's not a perfect diagonal like it's supposed to. The next example I found was from ABB Robotics. They have the little robot pinching hands, and I don't know if anyone here is thinking about going into robotics, but I would advise against it because this is the pinnacle of robotics. If you're going into robotics, I'm sorry, there's nothing left to do because this robot can do anything. This robot here is holding paper airplanes, but other videos, it's cooking pancakes. In another video, it's putting together an SD card. So, sorry, there's no more room in robotics. Both of these designs are very complex, very expensive, very beyond the scope of this project. But then I found my last example from David Balcom. This has used a suction cup to spin and rotate the paper and move it around, and folded the paper in a very interesting fashion. I have a video of that.
Sorry.
Sorry about that.
Gotta look through your PowerPoints, man.
I don't know how that works, how to make this work, but basically it has a suction cup here that can pick up the paper and move it around. Then it has a metal sheet here, so it would put the paper in this little crevice, pinch the paper so it can't move, and then this metal sweeper would sweep over the paper and make a hole. I liked this idea so much because it was so different from how we make origami. We make origami obviously by picking up the piece of paper with our fingers, folding it, and rotating it. This was a whole new way of making a hole. So, going on to brainstorming, here's what the robot needed to do. It needed to be able to move the paper, rotate the paper, fold the paper, crease the paper, which I'll explain the difference between those two things, and flip the paper. I define folding the paper as the motion of putting the paper over itself. This is folding the paper. Creasing the paper would be actually deforming the paper so it's permanently a different shape. And then lastly, flipping the paper is flipping the paper. So this is what I brainstormed. To move the paper, here's our sample paper. To move the paper, we had a linear actuator. I'll explain what that is later. Connected to this linear actuator is just a grippy finger like one of the examples. To rotate the paper, here, it's moving. To rotate the paper, I put it on a turntable that can rotate it. Then to fold and crease the paper, I have a more detailed demonstration later, but roughly we would have this bed with a little gap in it where two different metal edges could fold and crease it. And then to flip the paper, I had this little ramp. The idea was that the paper would go here and then be forced to curve along this ramp and then flip over. I decided not to go with this approach for multiple reasons. One of them is that this robot has no sensors. It doesn't really know where the paper is. It would just be following instructions. It's like making origami blindfolded and with gloves on. You can follow instructions, but if something goes wrong, you don't know something went wrong, so you just keep going. In this case, if the paper flips over and glides a little bit out of position, or doesn't flip over and just slumps back down, the robot would have no idea if it flipped it successfully or not, and would just keep going on with instructions. So I decided that this ramp was not a viable way to flip the paper. Folding and creasing the paper. I have a little demonstration here as well. The first step is that I have a paper here. I have the slit here. It's just a bar with a gap in it. Unfortunately, I don't have the folding or creasing edges. Those were the next parts to be printed, but I will simulate it here with just a metal ruler. So the first step is that the paper is moved on top of the gap, and then the folding edge, the red here, is lowered onto it. So I can do it right here. So after this, the paper is curled up just a little bit. It's not sustainable. It's pretty weak, as you can tell, but it is forced to curl up a little bit. Then the folding edge would be pushed up. The paper would be moved back so that the folding edge can be re-lowered, but just above the table. Not all the way into the slit, just above the table. That way, when the paper is forced to move forward, like this, the paper is forced to double back on itself. As you can see here, it makes a little bubble once it's folded back on itself, right along that fold that we already made. Last step, the creasing edge here in the orange would be lowered and to create, squish that paper to create a crease. I demoed it in class, kind of what you just saw here with just a metal ruler and a gap in the desk, and it did work, kind of. But it would work even better with origami paper, because origami paper is designed to hold creases even better than just normal lined paper I had. Next step in research, the paper. So a traditional origami paper is called kami paper, and it holds very well. So it would be able to use this folding and creasing edge even better than normal paper. Next, for motors, I was going to use the NEMA 17. It's just a normal stepper motor. A stepper motor is just a motor that is more precise than a servo motor. You can program it to go a certain amount of steps or rotate only a little bit to get more precise with your movements. For the folding and creasing edges, I would use a rack and pinion. A rack and pinion is a way to make rotational movement into translational movement. So in this case, this pinion or gear would move, which would cause this whole rack to move. If you just imagine this vertically, I would rotate a gear to make the folding edge and creasing edge move up and down. Then linear actuators. A linear actuator is just anything that creates translational movement. I would use this to move the paper side to side. There are multiple types of linear actuators. Hydraulic uses fluid, usually oil, to create movement, and they're best in high force situations. The pneumatic does the same thing, but with gas, and is best used for speed. And then piezoelectric is really interesting. You take a material and then electrocute it to slightly expand that material, just ever so slightly. So it's best used in high precision. Then there's mechanical linear actuators, which is actually an umbrella term for all these. So we have belt-driven, like up here, where a belt is rotated and anything attached to that belt would also move. They're best used in speed applications. Screw-driven, where a screw would be rotated and anything threaded along that screw would be moved. That's best used in precision. And then rack and pinion. I decided to go forward with the rack and pinion because I already am using it somewhere else in my project. So the pinion would rotate and the rack would move. So this brings us to some projects life lesson number 1. Engineering is not magic. In order to get to an objective, it's easy to just say, oh, I'll just have this part do it. Which brings us to life lesson 1.5. Okay, how? And this is what my advisor helped me the most with. I would say, I would want to use this part to do this, to serve this function, and they would go, okay, explain how. And that would help me rethink the situation and realize, oh, I need like 3 other aspects that I haven't thought about. So then I decided to, designing some parts. So here is the base of a turntable. I have it printed here. A motor goes in, a NEMA 17 would fit right into this square, where this lid would go on top, and this hole would slot into the motor, so this could rotate. Next is the folding area. This, I also have printed, would slot into the rotating, the turntable, and provide an area where the creasing and folding edges could operate. Then the turntable top is simple, it's just a circle. This is what the folding edge would look like. Notice it has a rack and pinion-like thing on the edges, and then just a narrow little ledge that would fit into this slot and force the paper to curl. And then the creasing is just the same thing, but thicker, so it could crease an edge. Scaffolding, this was just to make put a long in between the folding and creasing edges, so the edges would go straight up and down and not fall out. And then the folding edge is the last piece I have. That's what this is. It just has a small slit in it that the folding edge would fall into. I decided to make this a separate part and not incorporate it into the folding area because I knew this part would have a lot of trial and error. As you might have saw, this edge didn't fold the paper great. So I made it separate so I could fine-tune this part and only incorporate the perfect working folding slot into the folding area. This is what a final assembly would look like. Here's the exploded view and unexploded view. Which brings us to some projects, life lesson number 2. 3D printing is not magic. Going into this, designing those parts, I thought, okay, I designed the parts, I just put it into the 3D printer and it comes out perfectly. There's a lot of issues with that. Number one, printing takes time, lots of time, especially when you make parts so big. Prints can fail, especially when you make parts so big. And then, scaffolding is annoying. I did remove the scaffolding that was in this slot, but if you notice, there's still scaffolding stuck in these gaps here. And then, tolerance. I'll get to that later. Here's a time lapse of me removing the scaffold of my parts. I don't know if you'll play. Nope, you haven't did it yet. At this point in the year, we were nearing the end of presentations. All of my other stuff was printing, and I realized that I'm kind of running out of time. So I quickly designed what a linear actuator system could look like. So I redesigned the scaffold to go around what I have here, and then this is just a rack and pinion with a little stick going down to the turntable. Going back to life lesson number 2, 3D printing is not magic. This scaffold would be horrible to 3D print. There's no one plane where it could reliably print out of without adding a bunch of supports. So it would likely fail multiple times. My project timeline. So this is my initial timeline. Learning Python, researching elements, building the design, implementing code, then testing and improving. Here's what actually happened. I used Tinkercad to learn the coding and electrical at the same time, and then December, I used all of December to brainstorm the design of this. Then January, all of January and most of December as well, I spent designing the parts. I learned that designing parts takes a lot more time than just creating them in computer-aided design. In computer-aided design, you're just given the drawing and you can just recreate that part. Designing a part from scratch takes a lot more time. February, designing more parts in SolidWorks. March, panic. Oh boy, presentations are soon and I don't have all my parts. So, printing parts as fast as I can. During March, I looked into other ways of 3D printing parts. I looked into private companies, I looked into public libraries with 3D printers, but unfortunately, it was too late in the year, and it was too close to presentations, so anywhere I sent it would not print in time. Then April, I just made my presentations. So, what went wrong? Tinkercad wasn't very useful. It taught me more about electrical engineering than coding. The coding wasn't very applicable to what I was doing, that's why I decided to skip it and come back. Obviously, I ran out of time to come back. I would have chosen to do it, I wish I learned how to code while the parts were printing, so I could multitask. Next, printing took a long time. How I would fix this is I would make the parts less big. These parts, I think the base here took 28 hours to print, and it failed multiple times because it is so big, and it took up almost the whole base of the 3D printer. So scaling it down would help printing time and reduce the risk of failing. The reason I did print so big is because I thought once you make several folds on one piece of paper, the closer you get to a fold, the more resistance that paper is going to have. So if I could space out the folds in a paper by having a larger piece of paper, the resistance in that paper would go down. Parts don't fit together, which brings me back to tolerance. In Engineering 1, we designed a phone case, and my phone case barely fit my phone because parts slightly shrink after 3D printing. So right here, we have 2 slots, and right here we have 2 pegs. Theoretically, in a perfect world, they would be able to slot together. However, they do not, because I forgot to take into account the slight tolerance that these parts have. So I should have made the pegs slightly smaller. If I did have time, I could sand down those pegs and they would fit together, but I just ran out of time. So, project objectives. Rounding out my engineering, I'm going to say no. While I did learn about electrical engineering and a little bit about code, especially from Mark Wilber hack packs, I wasn't able to implement it. And if you go back to life lesson number 1, engineering is not magic. There's a big difference between learning something and implementing it. And because I didn't implement it, I thought it was unfair to say that I truly learned it. 2, creativity, I'm going to give myself a pass on. I did design all these parts. I was able to express my creativity through this project. 3, professionalism. Yes, I check my email now. It's great. I'm not missing things anymore. 4, time management. I'm on the fence about. Most of this year has kind of been a do or die kind of situation. And as you can tell, I did not die. But as you can tell from my project, I also didn't do. I'm kind of in between. So that one I left blank. And then stress management, no, absolutely not. This year has been very, very stressful. Here's my any questions?
Would you finish this project over the summer if you had work?
Yes, I really do want to. The problem is after I lose my school account, I also lose access to SolidWorks. So I could get the rotation system working, and I feel confident that I could make the creasing edge and folding edge system working, but the linear actuator system, that was just like throwing spaghetti at the wall, very quick draft. I don't think that would actually work.
Earlier in your presentation, you mentioned about the other linear actuator systems and why they make the benefits. I don't, maybe you mentioned this earlier, but I don't think you mentioned like the benefit for rats and things. And what is that?
It's a very simple system and very cheap. The other systems, like the hydraulic, you would have to buy because you can't. It's too complex to make yourself, at least for me. But a rack and pinion, I can make that. I modeled it up in SolidWorks. It's just a gear and a tube rack.
Okay, due to time constraints, we're going to have to cut that because the bell's about to ring. Okay, let's give applause to Riley.